Okay, it's been a while since we've done a video. Miss Siski came up with the great idea to do a joke at the beginning. So here's the beginning of my joke. Why did the mathematician go to the beach? Why did the mathematician go to the beach? And at the end of the video, I hope I'll remember to tell you the answer to that. So for chapter 10, for the start of chapter 10, we're going to talk about the properties of tangents. We haven't talked about circles much yet. As you know from kindergarten, a circle is, well, you probably didn't hear it this way in kindergarten, but it is all points equidistant from one point, which is called the center. And so we refer to this, we name circles based on their center. So this circle would be called circle P because the center is P. You can write circle P with a little circle with a dot in it, just the same way we draw a triangle for triangle ABC or a parallelogram for a parallelogram. Probably all these things that I'm about to tell you, you have heard of before, but let's get them down. A radius is a segment drawn from the center to any point on the circle. All right, and so that's going to be a radius. A diameter is, well, let's do a chord first. A chord is a segment that connects any 2 points on the circle. Now, a diameter is a chord, but it specifically includes the center, so it goes through the center. Still, it's a segment that connects 2 points on the circle, but it goes through the center. So that's a diameter. Okay, hopefully you knew that already. What you may not have known is secants and tangents. And so a secant is a line that goes through a circle at 2 different places. So there's a secant, and then a tangent is a line that only touches a circle at 1 point. It's really hard to draw a tangent, but the idea is that it only touches a circle at 1 point. Now, the point at which the line touches a circle is called the point of tangency. Not a big surprise. Okay, so there's a bunch of vocabulary that we'll need to know just to kick off our chapter on circles. There are, when you consider 2 circles, there are 3 different ways that they can intersect. You can have 2 circles that intersect at 2 points, kind of like when we were making our Venn diagrams the other day. Okay, so 2 circles can intersect at 2 points, or they can intersect at 1 point, which, surprisingly enough, when that happens, they're called tangent circles. Keep in mind that they could intersect outside of each other, or they could intersect inside each other. Again, it's really difficult to draw them exactly. Of course, it's difficult just to draw perfect circles. But when 2 circles intersect at exactly 1 point, they're called tangent circles. And the last possibility is when they don't meet at all. So let's say you have this situation. They don't meet at all, or you can have 1 circle inside the other. Actually, you could have it not be concentric circles. I intended to draw concentric circles here. And as you might deduce, concentric means they have the same center. So concentric circles are a possibility, or of course, you could have them just one inside the other. Again, that looks like our Venn diagrams. One inside the other without it touching. Okay, so those are our 3 possibilities. They could meet at 2 points, they could meet at 1 point, they could meet at 0 points. Now, we're going to talk about common tangents, and we're going to take all 3 of these possibilities. So we have, let's make sure that we're not distracted by this. Here we have 2 circles that don't touch. And so what you might want to do is pause the video and see if you can draw in all the common tangents for this situation, for tangent circles, and for 2 circles that meet at 2 points. So you might want to pause the video and try it on your own. So hopefully you paused the video. Hopefully you found 4 common tangents and again, I don't know that I can possibly draw them perfectly, but there are 4 common tangents when the circles aren't touching in that manner. There are 3 common tangents. Now, you might think that there are infinitely many lines that you can draw through here. Remember, they're meeting just at one point, but remember, it's got to be tangent to both circles. So there is only one line that you can draw through that point that is tangent to both circles. And then, of course, there's this one, and there's this one. So there's 3 here, and in this case, there are only 2. That and that. All right, so we have 4 common tangents. We have 3, and we have 2 common tangents. Okay, you'll notice that we're going to talk about a new theorem. You'll also notice, as I've said in the past, your book likes to name theorems. Most books like to name theorems with numbers. We will never refer to this as theorem 10.1, but just as a way to reference it. In a plane, a line is tangent to a circle. I don't know if we've talked about this before. This IFF stands for if and only if. Where am I going to write that? Let's just do this. IFF equals if and only if. It's a shortcut. It's not a Mrs. Trace shortcut. It is a mathematical. People kind of accept that as a shortcut, like the 3 dots for therefore and that kind of thing. So let me start over. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So in this case, if you know that line M, or either way, you could be given that line M is tangent, and if it's tangent, you know that this is a right angle here. Or you could prove, well, I can clearly see it's a radius, which, by the way, you can assume a radius. You can assume a chord. You can assume a diameter. And if it appears to be going through the center, you can assume that it is. So if I'm given a right angle here, and I can see that the radius is meeting this line at that endpoint of the radius, that could be a tangent. So line M is tangent to circle Q if and only if M is perpendicular to segment QP. And that's kind of some pretty powerful information that you can use in both proofs and algebraic problems. So here's an example of a problem you might have on your homework tonight. Is segment ST tangent to circle P? Well, I have some given information here. I have the fact that TP is 5 and this is 12 and this is 13. Well, 5, 12, 13 sounds familiar, I hope. It's a Pythagorean triple. With 13, the longest side must be the hypotenuse, which means this angle must be a right angle, which means yes, TS, or ST, is tangent to circle P. Okay? And, you know, there'll be varying degrees of difficulty. All right. The next thing we're going to take a look at is another example. And so in this case, you might be given a problem where you're given that point B is a point of tangency to circle C. So I know that by saying point of tangency, that means that AB is a tangent. It also means that this is a right angle. And so because I know it's a tangent, that is a right angle. And so because it's a right triangle, I can use the Pythagorean theorem. So I know that this squared is equal to this squared plus this squared. So I'm just going to write that down. Make sure it's clear that we have segment AC squared is equal to segment B squared plus segment AB squared. So let's just plug in the values here. Segment AC is not just 50, it's 50 plus R, so be careful about that. And then BC is R, and AB is 80. Now let's remember how we do this. Actually, I'm going to take R plus 50. Squared is going to mean R plus 50 times R plus 50. So we have to FOIL this. So first, outside, inside, last. And so if we combine like terms, all right, so I'm hoping that you might not need to come to the side and write all that out, although you might. It's been a while since we've worked with foiling and multiplying binomials. So here we take that r plus 50 squared. We end up with this after we FOIL it, and that's going to be equal to r squared plus 80 squared is 6,400. Now it's just an equation. At first you might think, uh-oh, quadratic, but when you subtract r squared from both sides, the r squareds disappear. So this is a lot easier than it looks. You're going to subtract 2,500 from both sides, you're going to divide by 100, and you end up with r is 39 feet. So the radius is 39 feet. Okay? All right, so the last thing that we have to talk about is another theorem. This theorem is going to say that tangent segments from a common external point are congruent. This is really helpful. What they're saying is if you know that SR is a tangent, and if you know that ST is a tangent, and you can clearly see that they are touching both at point S, we know that SR is congruent to ST. So if SR and ST are tangent to circle P, then those two are congruent. Of course, you know, there's all kinds of, again, the theorems are really powerful. You'll be able to use this a great deal for algebraic problems. And so if, let's say, you were given that RS was 3x plus 4 and RT was 28, ST was 28, you could, of course, set those equal to each other and come up with what x is. All right, I remembered. I hope you were thinking about why did the mathematician want to go to the beach? It's to catch some rays and become a tangent. To catch some rays and become a tangent. Okay, I know comedy's not my thing. I think I should stick to being a math teacher.